Welcome back to the video lecture series for Introduction to Data Programming using Scala. In this video we continue talking about spatial data structures, and in particular we're going to introduce the concept of a quad tree. So we've looked already at how we could use a brute force algorithm for finding neighbors. We've also looked at how we could use a grid for finding neighbors. And the grid was fine as long as our points were fairly randomly distributed. Okay? Everything was nice. But what if our data isn't randomly distributed? So what if, for example, we have an area of high density over here and an area of high density over here? Well, when we build the grid, it still gets quite a few cells in it, but unfortunately they are packed into certain areas. The vast majority of this space is completely empty. And so when I go to search for a neighbor for one of these, I have to search everything that's in the adjacent cells, and I'm definitely not going to get that order n performance that we were, well, I guess the order 1 performance. As long as the grid, as long as everything is random, the number of particles that I expect to search against scales, is pretty much a constant, because we're going to have on average 1 per cell. But if they're not uniformly distributed, if they are distributed with these high density regions, we have this problem where our grids have lots and lots of things around them, a large fraction of all the particles, and so it winds up actually going back to pretty much an order n. So how can we deal with this? We need something that's more dynamic and more adaptable than this, and that is kind of what a tree gives us the ability to have. So one of the trees that we want to look at for doing this is what's called a quad tree. And the idea of the quad tree is that it breaks the space into 4, hence the name, quad tree. And as long as there are more than a certain number of points in a region, it needs to break it up. How you determine that number of points can be done empirically. This example, the number is set to 1. So if there's more than 1 point in an area, it breaks it into pieces. So this is perfectly happy, and that's perfectly happy, but as soon as I put one more dot in here, it has to split something up. If I put another dot in there, it has to split that up. Another one there, it has to split that up. And indeed, if I do this where I draw a high density region up here, and then another high density region down here, you can see what happens is that these empty spaces wind up having very large cells in them, and they could have single particles in them, but they're not subdividing greatly. Whereas the regions of high density are subdivided so that when we go and we do a search for collisions, we're not going to spend much time, or a search for neighbors, we're not going to spend much time searching in these big empty areas. We're going to go down and be able to use the tree to limit where we're doing our search for. So that's the basic concept of the quad tree. You can also extend this idea into 3 dimensions, and then you get what's called an octree. This form of tree doesn't extend well beyond 3 dimensions because the next dimension up, we're going by powers of 2 here. In 1 dimension, this kind of is a binary tree. In the 2 dimensions here, it's a quad tree. In 3 dimensions, it's an octree. And in 4 dimensions, it would be a hexadecatree. So every node would have 16 children. In 5 dimensions, it would have 32 children. This really doesn't scale well once you get to those higher dimensions, but it's fairly simple. The way I've done this, now there are actually lots of ways to do quad trees and other spatial trees. The way I'm implementing this here, and that we're going to implement in the code, is what's called a region-based quad tree, where it always divides the space evenly based upon the region. You can also make it so that it would do the subdivision at a point. And so then it has to pick one of the points in here and use that point as where it's subdividing. One of the differences between those 2 approaches is in the region-based, all the data is in the leaves. Okay, so because this quadrant up here was centered there isn't any data associated with this. The data is associated with its child here, where this happens to be a leaf child, and the same thing goes for all of these. This is a little bit different than some of the other trees that we've seen, and I wanted to show it to you for that reason, to differentiate it. So in the next video we'll come back and we will actually implement our quad tree.